Okay, welcome to 4.0. We're going to do an introduction lesson to Chapter 4 where we're just reviewing some prerequisite skills before we get started. So the first skill that I want to review is solving polynomial equations. Now, we've already been doing this year, and you've been doing this throughout high school. In grade 9, we focused on solving linear, and that's when we rearrange and isolate the x. Usually it's an x. In quadratic, that's what we studied in grade 10, the first thing that you have to do is set it equal to 0 on one side, and then you start to factor. So you look for a common factor first, and then if it's possible, you factor it, so maybe you come out with like a couple brackets, and then you set each bracket or each factor equal to 0, and then solve those like a linear. You just rearrange and solve for x. If you can't factor it though, then you use the quadratic formula. And then in advanced functions, we started looking at factoring cubics. So for that, when we set it equal to 0, same idea as a quadratic, we look for a common factor first. If it's possible with a cubic, I would use factoring by grouping. It's like the middle step of decomposition factoring. When I have the 4 terms written out, I look for a common factor in the first 2 terms and a common factor in the second 2 terms. And if that works out, then that's going to be easier for me. Otherwise, if that doesn't work, we learned about the factor theorem and long division or synthetic division. And either one is fine as long as you know what you're doing. And then once we came out with those answers, we would factor each of those factors and then set them equal to 0 as well, like we did over here with the quadratic. Don't forget with a cubic that you usually end up with a linear factor times a quadratic, and then you have to factor the quadratic by coming over here and doing this guy. All right, the next skill I'm going to review is limits. So the first limit I want to review is when we have something like this, where if I sub -1 into this, I'm going to get 0 in the denominator. And there's nothing I can do to simplify this guy. If I factor the numerator, this one doesn't factor. It wouldn't cancel. There's no hole here. When I look at this, I recognize this graph. This here is telling me that there's a vertical asymptote. And they're asking me to actually investigate the x value that is the vertical asymptote. And so because of that, I need to use one-sided limits. All right, so I'm going to investigate the limit on the left side and the limit on the right side. And so this is one of the communication errors that I saw is some people want to just write down that I'm going to take the limit on the left and they put an equal sign here. You can't take the limit of nothing. So I can't just put an equal sign there. I have to say, what am I taking the limit of? Now this function has not been named, like sometimes it'll be named f at x or something, and I could just write that, but here it has no name, so I just rewrite the function. And now I can actually take the limit because I'm slightly to the left of -1. I'm going to sub that in. Now in the numerator, there's nothing offensive about getting close to -1, so I can just plug in -1. And in the denominator, I'm thinking about plugging in -1 from the left. So down here I had to think about the fact that I'm slightly off -1. Up here I didn't care because it doesn't matter if I get really close to -1 in the numerator. So in the numerator I end up with 1 plus 4. And in the denominator, if I put these guys together, they're going to get really, really close to 0. But because this -1 is slightly smaller actually than -1, then my 0 is also slightly smaller than 0. And now what I have here, I needed to figure out the number on top. I had to know that this was a positive in order to figure out what type of infinity this comes out to. So whenever I have a number divided by almost 0, that's infinity. But this is a positive divided by a negative, and so that's why my answer here is -infinity. And then we'll do the same thing on the right-hand side. So it's the same function that I'm taking the limit of. I need to write it down. And I can go ahead and take the limit because I'm going to be slightly on the right of -1. Again, in the numerator, there's nothing offensive about plugging this in, so I don't need to worry about it being slightly positive or anything like that. In the numerator, though, I will think about that. So in the numerator here, I've got 1 plus 4, that's 5. And in the denominator, I've got something slightly bigger than negative 1 added to 1. And so that's going to be really close to 0, but slightly bigger. And now what I've got here is a positive divided by a positive. So I know that my answer is going to be positive. And then 5 divided by almost 0 is going to be infinity. And then I can say that this limit does not exist, but in this chapter, we're specifically going to be looking for these types of infinity that we get. We're going to be looking at the behavior close to this vertical asymptote, so the conclusion will be a little bit different here. Now I'll be looking at what's happening on either side of negative 1. So you can imagine on the graph here, I've got my vertical asymptote, and what I figured out is on the left, the graph is heading to negative infinity, and on the right of negative 1, the graph is heading to positive infinity. So I've actually figured out some of the graph properties. All right, the next section we need to review is end behavior. So we learned about end behavior in advanced functions, and it looks like this. As x approaches negative infinity, y approaches, and we want to know like what are the heights of the y values as I move to the left of the graph, right? Because I'm going to negative infinity. And then we do as we move to the right. So as I head to positive infinity on my x's, how far up or down am I heading? And in advanced functions, we looked at the properties of some polynomial functions. So remember that when I have a polynomial function, that's what I have here with f and g, the ends of a polynomial always go to positive or negative infinity. So imagine some of the polynomials that we know about. We've got the line, we've got the parabola, we've got the cubic, we've got the quartic, which, and so the cubic can look like this or it can look like this. And then we've got the quartic, which can kind of look like the flattened out parabola, or it can look like the W, right? So we've got, these are kind of our family of polynomials. Notice though that the ends are always heading up or heading down. They're not heading towards like a horizontal asymptote or anything like that. So let's remember, how do I figure out which ends are going where? So what I look for is the lead coefficient. So the lead coefficient here is going to tell me which way I go on the right side of the graph. So because this is negative, it tells me I'm going down on the right. So you'll notice in my examples here, I drew them all going up on the right. These ones would all have positive lead coefficients. And then the next thing that I look at is the largest degree, or the largest exponent. So this one here, it's an even number. And that tells me, so look at here, I've got an even exponent, right? This would be degree 2, this would be degree 4, this would be degree 4. Notice that the end behaviors match in all of these. Whereas here, when I have a degree 1 or degree 3, the end behaviors are different. They're opposites. So even degree tells me that I have matching end behavior. I'm just going to use a little short form there for behavior. So that's going to help me come up with my statements. So I'm going to think about, well, what's happening on the left and what's happening on the right. So remembering here that this is the left and this is the right. I'm going to start with the right because I know that on the right it heads down. So starting with the right here, I know it's going to head down, and then I use the degree to help me fill in the other one. It's an even degree, so it matches, so I'm just going to write down the same thing. All right, moving on to the next one here. Again, I look at the leading coefficient, so the coefficient with the largest exponent. Here it's positive, so that tells me it's going to go up on the right. And then I look at that degree. It's an odd number this time, which tells me that I have opposite end behaviors. They're going to do different things on both sides. And so I'm going to set up my statements again. You don't have to do them in this order. Like if you want to put the right one first, that's fine. I always do it first, but I write it second. And you can write the positive in front of the infinity like I did here, or over here I did not. That's fine too. So again, just thinking in my head that this is the left and this is the right, and I know because of the lead coefficient being positive, I know it goes up on the right. So I know that this guy here is heading to positive infinity, or again, you could just write infinity. And then the odd degree tells me that I have opposite end behavior. So if this one was positive, I need this guy to be the opposite, so it's negative infinity. All right, and then the last thing I want to talk about, we're going to also look at the graphs of rational functions in this chapter. So rational functions have vertical and horizontal asymptotes that I need to think about, and sometimes even oblique, and we're going to look at that a little more carefully in calculus. So vertical asymptotes, to find the equation, we just set the denominator equal to 0 and solve. And then for horizontal asymptotes, there was an advanced functions trick. Now, you can use this trick to kind of justify that your answer is correct, like in your head to yourself if you're checking your work, but we're not going to use this trick anymore. But I just want you to remember that if the degree of the top or the degree of the numerator is less than the degree of the bottom, then the horizontal asymptote will be equal to 0. So thinking about an example of that would be if I had the degree of the top is less than. So if I have like an x on the top and an x squared or an x cubed or an x to the fourth, anything like that on the bottom, then I'm going to have a horizontal asymptote here of y equals 0. In the second case, if the degree of the top is equal to the degree of the bottom, so this time let's say I've got like 2x squared minus 7 over 3x squared plus 1. In this case, the degree of the top and the degree of the bottom are both 2. So to find my horizontal asymptote, I divide the leading coefficients. So the leading coefficients here are 2 and 3, and my horizontal asymptote is 2/3. And then in the third case, if the degree of the bottom, or sorry, the degree of the top is bigger than the degree of the bottom, there's no horizontal asymptote. So if I have something like y equals 3x cubed minus 2x squared over x squared plus 7, this guy here does not have a horizontal asymptote. This one has an oblique asymptote here, and we're going to talk more about how to find that throughout this chapter. If the degree of the top instead had been a difference of 2 compared to the bottom, there would be no oblique asymptote either. All right, have fun with the homework for this.